Okay, so we ended class last time and I had introduced L'Hopital's rule. And today we're going to go into it in depth. But I wanted to kind of take some time to talk about this idea of an indeterminate form. All right, so when we take limits, all right, the important word there is the limit, right? So if you're taking a limit, I will say in the limit, when I say that in the limit, what I mean is we're applying a limit to something, and this is the form, this is what it's turning into when we take a limit. If we get any of the forms over there, so I'm going to write them there so I can refer to them today, but they won't be on camera, so I'm going to also put them here. We know how to deal with these two forms. We've seen this before, right? And what we normally did in those cases was some algebra or some sort of trick, right? Depending on the limit, we would adjust our technique depending on what we see. An example of each of these specifically would be something like limit x goes to 2, x squared minus 4 over x minus 2. I think I gave something like that similar to that in class last time, right? If x goes to 2, we're going to get 4 minus 4 on top, 2 minus 2 on the bottom, we're going to get 0 over 0. What we normally would have done is some algebra. But the important thing is that this is a form that we cannot determine by just looking at it, right? It's indeterminate. Infinity over infinity is another indeterminate form. We also dealt with infinity minus infinity. That happened in the past also, and I'll give you an example of this. You had one similar to it on your first test. Limit x goes to infinity. Let's say x minus square root of x. So you have infinity, take away infinity. Anyone remember how we did something like this?
You had to do the 1 over x something.
Yeah, you like factored it. Here you would like pull something out and turn it into a product, and then you would get to the answer. All right, so my point here to start is just that there are 3 indeterminate forms that we are familiar with already. But there are several others that we need to be able to deal with. One of them being 0 times infinity. And I want us to think deeply about this, all right? 0 times infinity. An example of this would be, let's say limit as x goes to infinity of, what can I do here? How about this? Sine of 1 over x times e to the x. Take a look at that right there. What's happening here as x goes to infinity? Well, what's 1 over an infinitely large number? That's going to get smaller. It's going to go to 0, right? What is sine of 0? Sine of 0 is 0. So this right here is approaching 0, right? So this number, as I plug in values of x, that number gets smaller and smaller and smaller and smaller. Are we saying that it is actually 0? No, we're saying it heads to 0. So this is a very small number times e to the x. So what happens as x goes to infinity? Well, e to the infinity, that means you look at the exponential function, it's, as you go to the right, the function is growing, 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 and becoming infinitely large. Agreed? So we have something that's getting very small times something that's getting very big, and that is still an indeterminate form. We don't know, right? Give me a very, very small number. 0.00001. Happy with that? If you multiply that times a billion to the billion to the billion power, then this number would be a lot bigger than this one, right? So when we say it's going to 0 and this one's going to infinity, it's kind of like who wins? One of them is getting small, the other one's getting big, but you can't just look at it and tell who wins. This number could be really, really small, and this one could be big, but not that big compared to how small this one is, right? Do y'all understand what I'm saying? Yes? No? Yeah? Okay, so when you see 0 times infinity in a limit, right? I erased it. In the limit, if you see that, we don't know. We have to do something to actually figure out what the answer is. All right? Do you buy that?
Yeah.
Okay. All right, now the other 3 forms, indeterminate forms that we have here, we need to analyze and think about also. Let's look at this 0 to the 0. So let's say we take a limit and we get 0 to the 0. And I'll give you a specific example below. Let's just do this one. Sine x to the x. So as x goes to 0, right, as x goes to 0, what does the sine function do? It goes closer to 0, right? So this is headed towards 0, raised to the, obviously, x is going to 0, so 0 to the 0. Now, why is that an indeterminate form? Anything raised to the 0 should be 1, right? But see, the thing is, it's not 0. It's close to 0, but it's not. Understand?
Yeah.
On the other hand, if I take 0 and raise it to any number, it should still be 0. So you have a tug of war happening here. The base is like, I would like to be 0, right? I'm trying to get smaller and smaller and smaller. Please let me be small. And then the exponent's like, but wait a minute, I'm getting small too, and the rule for me is that if I'm small, if I'm 0, I turn this whole thing into 1, right? So do you see that there's some conflicting things happening there? It's indeterminate. So we'll have to investigate this further to see what that actually does. All right? Let's look at why didn't I put 1 to the infinity up there? Did I put it on the notes? Yeah, hold on. Oh, there it is, 1 to the infinity. I forgot to put it here. 1 to the 0. Why did I put 1 to the 0? I meant to put infinity here. Oops. That's infinity. Okay, so that's an indeterminate form. We're going to leave this as an open question. Now let's look at infinity to the 0. So the base here wants to get really big, right? The base is trying to get bigger and bigger and bigger. But that exponent again is 0. And we just said that anything to the 0 should be 1. So this is kind of the opposite of what just happened. Instead of the base trying to get small and go to 0, and the exponent trying to turn it into a 1, this is the base is trying to get big, but the exponent's trying to force it to go back to 1. Understand? Indeterminate form. And then the last one we have is 1 to the infinity. So that you would think is just 1, right? And I agree with you. 1 to any power should be 1. But the problem is, this 1 down here is, we're not saying it's 1, we're saying it's approaching 1. Okay, it's approaching 1. So if this number is just a little bit bigger than 1, and we raise it to an infinitely large power, it's going to start to try and make it bigger. The key is that this base is not 1, it's close to 1, and that the power wants to just make it bigger, right? Multiply it times itself over and over and over and over, so it should get larger. Does that make sense? So this again is an indeterminate form. I'll give you an example of this one. Limit. This is a famous limit. We will do this today. Right there. Does anybody know what that is? Like if, no, I doubt you would, but let me.
Is it a decay or a growth?
Actually, it's neither, because this is not an exponential function, because the base is not a constant. If this was like, 4 to the x or something like that, then that would be growth or decay.
So that one isn't turned into 0.
Let's see what happens here. As x goes to infinity, 1 over x goes to 0, right? But it's not 0. It's very close to 0. So if I take a number that's really close to 0 and I add it to 1, that number is going to be really close to what? 1, right? So the base of this is really close to 1. And then the exponent is what? Getting infinitely large. And that is actually a problem, all right? So let's just do, if you have your calculators out, let's just do a little exercise here. All right, let's see who's quick with their calculators. Let's take a look at this. Let's look at this f of x. I'm going to define a function. I'm just going to come in here and call this function 1 plus 1 over x to the x. I'm going to call it f of x. And so I'm going to try and get an idea of what this is doing, right? And then we're going to ask ourselves, what happens as x goes to infinity? So let's try something. Let's plug in some values. We'll do like a good old t-table. X here, f of x here. Let's start out with 1. What would happen if you plug in 1? 1 here, right? And then you get what? 1 over 1, that's 1. 1 plus 1, 2. 2 to the first power? 2. All right, we got 2. Great, that was wonderful. Now let's plug in 2. All right, when we plug in 2, 1 over 2 is 2. That's 1/2, 1.5. What's 1.5 raised to the 2? 2.25. All right, let's get bigger, because we're supposed to go to infinity, right? And we're sitting here at 2. Let's go to 10. Now, this is where you'll need your calculator. So 1/10 plus 1 is 1.1. Raise that to the 10th power. 2.59. 2.59, thank you. Let's go bigger. Let's go to 100. X is 100. So 1 over 100 plus 1, 1.01, raised to the, what is it? 2.70. All right, let's get like crazy now. Let's go out to like 10,000. Try 10,000. $2.71. Any more decimals?
Yeah, 2.718.
2.718. Let's go a little bit more. Let's go to 1 million. And give me all the decimals that you have. All right, on the next one.
Is it supposed to be approaching Euler's number?
It's supposed to be approaching what?
Euler's number?
It is. It's E. What do you get? 2.7?
1, 3, 2, 8.
Okay, that's good enough. If you keep going and you start putting in bigger and bigger numbers, it's actually going to converge. This thing is going to head towards something. It has a limit. The limit exists. This doesn't go to infinity. It doesn't go to 0. It doesn't go to 1. It actually goes to E. And remember, we talked about E is approximately 2.718, right? You could actually define E to be this limit. Like if someone asked you right now, hey, what is E, that number? What is it? You could say, oh, E is just the limit as x goes to infinity of 1 plus 1 over x to the x. That's what it is. If you look in a textbook, that's the definition of E. And I told you about this, right? Okay. That is a definition of E. Now, I'm going to prove that to you later. Like, I'm going to show you. We're going to do that limit in a little while. We're not ready for it yet.
Domain restrictions on that?
Well, x can't be 0.
Or less than 0?
Yeah, but see, we don't care. It's a limit, and we're letting x go to infinity.
I just graphic.
Yeah, you won't have stuff from 0 to the left. You won't have anything. Okay, so that is the 1 to the infinity. Now, what we have to be careful with is getting this false idea that anything we see that involves 1, 0s, or infinity, or that they're all indeterminate forms. Like I had put up here just a second ago, 1 to the 0. Let's say we take a limit and we get 1 to the 0. Is that an indeterminate form? No. The base is sitting there saying, hey, I want to be what? 1, and the exponent is saying,
It should be 1.
I'm going to help you, right? I'm going to actually help you become 1 too, because when you raise something to 0, it tries to turn it into 1. So they're both trying to be turned into 1 at the same time. Does that make sense? This is not an indeterminate form. If you see this limit, your answer is 1, and you're done. There's no work. How about this? How about 0 to the infinity? Is that indeterminate? It's not up there, right? Why is that not indeterminate? It's not.
Big number and that one 0 can't be 1.
What is the base trying to do?
Trying to go to 0.
Trying to go to 0, right? That means it's a really small number. And then what happens if you raise a number to a big power? Does it always get bigger?
No. If it's like a fraction.
Yeah, take a fraction like 1/2. What would happen if you square it? You get 1/4. It got smaller, right? If I take 1/3 and I cube it, right? That's going to be 1/27. That's even smaller than it started out as, right? So if the base is trying to be small, right, but it has to be going to 0, and the exponent's getting big, it's kind of like the base is like, the base sitting there. I like to think about these things talking to each other. Okay, so the base is sitting there like, I want to be small, and the exponent's like, well, I'm going to help you get there because I'm going to start raising you to powers. You can get smaller, smaller, smaller. So you're going to go even faster. So what would be the answer to this? 0. That'd be it. There's no work to do. All right. That's why it's important for you to understand. You could memorize these. Okay, you could memorize them. That's fine, but it's more important, I think, in my eyes, for you to understand what's happening, because that will always follow you, right? You'll always remember. If you can understand what's happening, then it's easier to remember. What else? Something like this. Infinity to the infinity. That would not be an indeterminate form. Base wants to get big. The exponent's going to keep multiplying it times itself. It's going to get bigger and bigger and bigger. That's going to be infinite. Something else. 0 to the infinity. 0 over infinity. That is not indeterminate. Think about it this way. If the numerator is fixed, remember from our limits before, if the numerator is a fixed number and the bottom gets smaller, what happens to the fraction? No. 4 over something that goes to 0. If 4 is 4, doesn't move, and the bottom gets smaller, what happens to this fraction? Gets bigger, right? We did this before. When we had fixed over 0, that was the one where we had 3 possibilities: infinity, negative infinity, or does not exist. That ring a bell? Yeah. Okay. So look at this situation right here. Infinity times over 0. You could rewrite this way. Look at it that way. Do you agree that kind of looks like that? This one is fixed over 0. Fixed over 0 should go to what? Infinity or negative infinity? What's something that's infinite times something that's infinite? Infinite, right? It's going to get bigger and bigger and bigger. So this would be infinite. How about if I flip them over? Try and do the same idea here. Try and write this as 0 times 1 over infinity. What's a fixed number over infinity? That's going to go to 0. What's 0 times 0? 0. Should be going to 0. All of these are not indeterminate forms. There's one more I can throw up here that I think is very obvious. Infinity plus infinity is infinity, right? All right, so now what we're going to do is we're going to use L'Hopital's rule, which I'm going to state what it is in a second, and then we're going to start working through these limits. And since we've done these first 3, right? We've done those first 3. We'll do a few of those, and then we're really going to want to focus a lot of our attention on those last 4 that I didn't circle. 0 times infinity, 0 to the 0, infinity to the 0, 1 to the infinity. How do we attack those? And it turns out that in order to attack these 4 that we haven't really looked at very much, we're going to need to be real good at the 0 over 0, infinity over infinity. And then we'll throw in some other little tricks and stuff, and it's all going to be good. All right, so what does L'Hopital's rule state? Yeah, it's just a completely awesome rule. It says that, where the heck? There it is, real big there. Basically, it says if you're taking a limit, doesn't matter what the limit's approaching, okay? If the form you're getting is 0 over 0, if that's what you're getting in the form of the limit, then if this limit exists, all right, if it actually goes to a number, then that will be equal to, the limit you're trying to look for is equal to the same limit going to the same place, but instead the derivative of each one divided. Not the quotient rule. You just take derivative of the top, derivative of the bottom, you look at that answer, you take the limit again, and you hope that it's easier than what you were looking at before. Okay? This is not an easy rule. This L'Hopital's rule is not an easy rule to prove, all right? Where is it? Oops. And that's it right there, L'Hopital. Now, it also says that the same thing works if you have infinity over infinity. And it doesn't matter if it's plus or minus infinity on top or bottom. If the top's going to some sort of infinity and the bottom's going to some sort of infinity, you can still apply the same rule. All right? So the key to using L'Hopital is that we have to have one of these two. If you do not have one of those two, you are not allowed to use L'Hopital's rule. Is that clear? No. You have to have that. So if we ever get this form right here in a limit, 1 to the infinity, you cannot just start doing L'Hopital's rule. You must somehow convert it into 0 over 0 or infinity over infinity, which we'll do, just you have to be patient, all right? So let's start with our first example. Let's take the limit as x approaches 1 of natural log of x over x minus 1. Yeah, that's good. So what happens here? X goes to 1. What's natural log of 1? 0. You have to remember that from the graph of natural log. Here's the graph of natural log. It hits here at 1, 0. When you plug in 1, it spits out 0. All right? So the top is headed towards 0. The bottom is headed towards 0. So that's bad. Now, normally this is where we would do some sort of algebra, right? And there's actually nothing you're going to be able to do algebraically. There's just nothing you can do. You can't come in here and like do some sort of weird conjugate, or there's no factoring you can do. You're stuck, all right? And so our only choice right now is to do L'Hopital. So I'm going to apply L'Hopital's rule, which means that I can do the same limit, but I get to take the derivative of the top and the bottom separately. So what is the derivative of natural log of x? 1 over x. And then what is the derivative of x minus 1? 1, right? That's it. Now, did I show you all last time the symbol that we used to let everyone know that we just used L'Hopital's rule? I didn't talk about that? Okay. It's very important that you somehow illustrate in your work that you used L'Hopital's rule. Different textbooks do it different ways. A lot of textbooks, what they do is they put an H right here above the equal sign to let everyone know they use L'Hopital's rule. Sometimes they'll put a circle around the H. And I've even seen books, instead of putting an H with a circle, use an L with a circle for L'Hopital. The H for Hopital, right? Like, I don't know, it's French, so they just left off. A lot of books leave the L out and they just put the H. I've always used the L. You use L or H, but you have to somehow designate to whoever's looking at this, including yourself, what you just did. All right? You were allowed to use L'Hopital's rule here. Because you have 0 over 0, you apply the rule. Here's the application of the rule. This limit becomes this limit. And now look what happens when you let x be 1. You don't have any problems anymore, do you? Your answer is just 1. And that's it. We're done. Did we talk about the sine x over x last time? I watched the video of this class, but I've already forgotten. What the heck? Okay, well let's look at this real quick. This won't take long. This was one of those very, very important limits. When I first started talking about limits in this class, I said that you must memorize this one, right? And I said, yeah, everyone came in, took a quiz. Remember there, it was on your quiz at the bottom. Everyone got it right. It was 1. Yeah. Okay, so this is 1. Now, you were supposed to just take that on faith back then. And I said the proof of it's very, kind of nice. You could come by my office, I could show you. There's a geometric proof for this. It's really cool. It uses what's called the squeeze theorem. But we can do it with L'Hopital's rule now. So do we have the form that we need to use L'Hopital's rule? Sine of 0, 0, we get 0 on top, 0 on the bottom. We do have the form we need, so I'm allowed to use the rule. Here comes L'Hopital right here. And derivative of the top, cosine x, derivative of the bottom, 1. Don't use the quotient rule, right? I've been beating it into your head like, you need to use quotient rule, right? Like, you got to make sure you use quotient rule. We're not taking a derivative of a function, are we? No. We are looking at a limit, right? We're looking at a limit, and it just turns out that to do limits now, we can actually use the derivative, but not the derivative the way we've used it in the past. It's the derivative of top and bottom separately. So now cosine of 0, 1, 1 over 1, 1. Now look, our answer is not always going to be 1. It's just a coincidence that these are both 1, all right? All right, let's look at another one. Let's change the limit. Let's go to infinity instead. Let's do natural log of x over the cube root of x. So where's the numerator headed? When we say natural log of infinity, what does that mean? That means you're looking at the natural log function, and you're asking yourself what happens as x, right? X goes to infinity. So start moving out this way forever. What happens to the function? What happens to natural log of x as you move to the right? No, not the natural log function. I kind of misdrew it here. It goes to infinity. It grows, okay? It grows kind of like the exponential function grows. It just doesn't grow as fast. So it'll keep growing, keep growing, keep growing. So as x goes to infinity, the natural log function goes to infinity also. And then on the bottom, the cube root of infinity should still be infinity, shouldn't it? Yeah? So we have infinity over infinity. Now L'Hopital. So the derivative of natural log of x is 1 over x, right? And then what's the derivative of the cube root of x? Cube root of x, we want the derivative. That's the same as x to what power? 1/3 power. We want the derivative. What's the derivative of x to the 1/3? 1/3. X to the negative 2/3. Very good. And then can I rewrite that as 1 over 2x to the 2/3? Is that all right with you? I don't like the negative exponents. I don't. So I'm just going to write, yeah, that should be a 3. Thank you. Saw some weird looks on your faces. I'm glad y'all said something. Okay, so that's 1/3. This dropped down, and we're good? Yeah. That's derivative of cube root of x. So down here, I'm going to write 1 over 3 x to the 2/3. Now this next step is critically important, all right? Critically important. Right now, if you take the limit, what would you get? What's this? 1 over infinity would go to 0, right? 1 over 3 times, that would be infinity again, right? So that's 0, right? You get 0 over 0, wouldn't you? 0 over 0, you could use L'Hopital again. Do y'all see that? Yeah. Don't do it. Because you can only use L'Hopital's rule if after you've simplified it algebraically, you still get 0 over 0. Or infinity over infinity. We have not simplified this algebraically. Look at this. This is a fraction over a fraction, right? And I can flip this one up, and let's see what happens. We get 1 over x on top, but then I'm going to multiply that times 3x to the 2/3 over 1. Y'all know what I did there, right? Just the algebra of flipping that up, division is the same as multiplication of the reciprocal. Yeah? Okay. And then, at this point, I continue. Just rewrite the limit. X goes to infinity. All right, I'll have a 3 on top. Let's see. I can put, let me just write it. X to the 2/3 over x. That's where I am. And again, don't go let x go to infinity over infinity yet. You can simplify this. What is that? That's x to the negative 1/3, right? You take 2/3, you subtract 1, that's x to the negative 1/3. Agreed? With a 3 in front. So this becomes limit x goes to infinity, 3 over x to the 1/3. I just wrote the x to the negative 1/3, I dropped it down. Now let x go to infinity. What do you get? Fixed over infinity, which goes to 0. What's the moral of the story? Yeah, you want to make sure that you just don't start applying L'Hopital over and over and over just because you keep on getting 0 over 0 infinity over infinity. Make sure you look at it algebraically first. If it cleans up, that's the direction you want to go. If you did L'Hopital again here, you might accidentally, coincidentally get 0, but it's not guaranteed. Most likely, if you did L'Hopital again right here, you would get an incorrect answer. Understand? All right. How about this one? X goes to infinity. Yes.
You were writing the L over the equal sign. Now, when you went to the next step, I noticed you didn't put it. You only have to do it for the step.
Just that first step when you use the rule. Uh-huh. All right, how about this one? X to the 4th over e to the x. So what happens as x goes to infinity here? Infinity to the 4th power, that's infinite on top. And on the bottom, what's e to the infinity mean? Yeah, this again is where you need to look at the graph if you're having any trouble with it. Right? When you say e to the infinity, right, what you really mean is this. This does cause students problems, so let me just be real clear. This is what we want to know, right? That bottom piece? So let's just look at that for a second. This is saying, hey, look at that function, e to the x, and tell me what happens when x goes to infinity. So here's e to the x, let x go to infinity, what does this do? Goes to infinity. Bless you. All right. So can I use L'Hopital? Yes. So I do L'Hopital's rule. And when I do it, I get on top 4x to the 3rd, and on the bottom, well, yeah, derivative of e to the x is itself. Right? We still have the same issue, don't we? If we let x go to infinity, we're going to get infinity cubed times 4, it's still infinity, over infinity again. Yeah, there's no algebra I can do on this to make it cleaner, right? Like on the last problem I flipped and I got things to kind of clean up. Here I can't do anything algebraically. So because it's infinity over infinity still, right? And only because it's still infinity over infinity, I can apply L'Hopital's rule a second time. So I'm going to say this equals, by L'Hopital's rule again, well, let's actually do the rule, sorry. What's the derivative of the top there? 12x squared over e to the x. And you have the same problem, right? And do you see what's going to happen? Eventually, what's going to happen? You're going to get a fixed number on top, right? The power is going to keep dropping every time we do it. So let me do limit again. L'Hopital, x goes to infinity. 24x over e to the x. That's still infinity over infinity. I haven't been writing this, but if you're keeping score, this thing was still infinity over infinity. This one was still infinity over infinity. This one was still infinity over infinity. And then now at this last step of L'Hopital, you get 24 over e to the x. And now that's fixed over infinity. Fixed over infinity, that goes to 0, right? So this limit is 0.
So at the beginning, after you do it the second time, wouldn't it be pretty recognizable, but that's going to happen?
Yes.
You want all that work?
Well,
Can you tell that it's just going to keep dropping and it's eventually going to be fixed over infinity?
Yeah, that's a good question. Like if I had put x to the 400th power, right? I wouldn't expect you to do 400 derivatives. You would see the pattern. The purpose of this problem is to establish in your mind that you would see this, right? And you would just state it. It's more of a learning thing here, that you can repeat L'Hopital's rule if need be, all right? And that sometimes you can see while you're doing it what's going to start to happen. And you just want to be able to recognize that. What would happen, though, if I flipped it over? What would happen if I put the e to the x on top and I do x to the 4th on the bottom? You still have infinity over infinity, right? You do L'Hopital one time and these would flip places, right? So these would become e to the x over 4x cubed, right? You would still have infinity over infinity. Do L'Hopital again, this would be e to the x, this would be 12x squared. Still have infinity over infinity. You would do L'Hopital's rule again, you'd get e to the x over 24x. Still have infinity over infinity. Last step, you would get e to the x over 24. You no longer have infinity over infinity. But you have infinity over fixed, right? In other words, forget the 24. It's not moving, right? It's just there. What happens to e to the x as you go to infinity? It becomes infinite, right? Divide that by 24, you still have infinity. This becomes infinite. It goes to infinity. See the difference between those two? All right, how about this one? Let's go, I'm just going to do x to make this a little easier. X e to the negative x. X over e to the negative x. So instead of x to the 4th, I just put x to make our lives a little nicer. And instead of e to the x, I put what? E to the negative x, right? How does that change things? This goes to infinity, right? Over, what does e to the negative x mean? It's important that you understand what this means. What does e to the negative x look like? This is e to the x, right here. This is e to the x, right everyone? That's e to the x. It flips it, not along the x-axis, along the y-axis. E to the negative x is a reflection of this. This is college algebra, so I know it's been a while since you've done reflections. But when you put a negative up in front of the x, not in front of the function. If you put the negative out here, it flips it over the x-axis. If you put the negative up on the x, it flips it over the y-axis. So e to the negative x looks like this. And now you're asking what happens as x goes to infinity. Where does it go? Heads. Where does it head? To 0. It heads to 0. So the top is going to infinity, the bottom is going to 0. Is that an indeterminate form? Can we use L'Hopital on this? No, you cannot, but you should be able to tell me what this is. That's infinity. We just did this a second ago. If the top is getting big, right? What happens to a fraction when you divide by a small number? It gets bigger, right? So this guy's trying to get big. The denominator's like, I'm going to get small so you can get big faster. So this is just going to be infinite. Understand? So this is going to go to infinity. Now let me show you a different way you could have done this problem that probably would be a little easier to see. Yeah, why not bring that negative exponent on the bottom, e to the negative x, bring it up as e to the x. Wouldn't that be the exact same problem? Now tell me what happens. This goes to infinity times this goes to infinity, because now you're looking at e to the x again, the red one. So infinity times infinity is infinity. So you get the same result. So if I were doing this problem, I would have done it this way. But I showed you this because I want to make sure everyone's comfortable with the idea of what e to the negative x looks like. That it's this one. Any questions? All right, let's get some trig stuff in here now. Limit x goes to 0, tan x minus x over x cubed. Is it 0 over 0? What's tangent of 0? It's 0. How do you know tangent of 0 is 0? Calculator said so? This is the graph of tangent, everyone, right? It has asymptotes where? Negative pi over 2 and pi over 2. Tangent of 0 is this point right here, and you can see it 0. So tangent of 0 is 0, and then take away 0 because we're plugging in 0, right? So you get 0 on top, and you get 0 on the bottom, don't you? I can use L'Hopital's rule. So bring in L'Hopital equals limit x goes to 0. All right, we need to remember some derivatives. Derivative of tangent x. Secant squared x minus 1. Secant squared x minus 1 over derivative of the bottom, 3x squared. There you go. Let x go to 0 again. See what happens. How do we do this? Secant squared of x. If we plug in x as 0, we do secant first and then square it. So just remember, secant squared x equals secant x squared, right? That's what that means? What is secant? Don't show this message again. There we go. What is secant of 0? Yeah?
I don't know what it is, but I see the secant squared x minus 1 is tangent squared x.
Yes? You could do that.
0.
That's fine.
Tangent of 0, 0.
That's fine. But if this was secant squared x minus 4, let's just say, then we just need to make sure that we know how to get this. Here's the way I would do this. If you don't know what secant of 0 is, just go back to the definition of secant, which is 1 over cosine. Right? That's what that means. 1 over cosine is secant. That you would have to know. So cosine of 0 is 1. 1 over 1 is 1. 1 squared is 1. So the top left corner as x goes to 0. This top left corner is 1. 1 minus 1, 0. Over, of course, 0 squared times 3. That's still 0. So we have 0 over 0. I don't see any algebra we can do there because there's no way we can combine this x squared up here to get things to cancel. Right? So let's just go again. L'Hopital. I'm sorry? Yes, that's what we were just saying. That you could rewrite secant squared x minus 1 as tangent squared x. You could, but I'm not going to do it. I'm just going to leave it as it is. What is the derivative, though, of secant squared x? Good. Chain rule, right? First, we're trying to take derivative of secant x squared, right? First, the 2 comes out. So 2 secant x times, now the derivative of what's inside, secant x tangent x. So we're going to have another secant x tangent x. Are we done taking derivative of this? Let's see, the 2 came out, right? We got that? 2 times this to the first power, that's out there. Derivative of the inside, secant x tangent x, we're done, right? Now, derivative of negative 1? 0, so that's it on top. How about derivative of the bottom? 6x, right? Ugh. Ugh. L'Hopital was here to help us, wasn't it? Okay, let's just check. Let's let x go to 0 here. If x goes to 0, secant of 0 is 1. Secant of 0 is 1 again. So this is 1, that's a 2, but tangent of 0 is 0. So we have 0 on top, and on the bottom, 0. Yeah. Now, this next step is extremely important, all right? This is an extremely important step. We can use L'Hopital right now, can't we? But I don't like the idea of using L'Hopital because I'm going to have to do a triple product rule, or I could put the secants together and then I'd still have some product rule, but I'd have chain rule, all right, when I go to take a derivative. So because this is a limit, I want to remind you about a property of limits. Doesn't matter what your limit is. If you have two functions being multiplied together inside of a limit, you are allowed to split this up into two limits. You are not allowed to do this when you're doing derivatives, right? If I have two things being multiplied and I tell you to take the derivative, you have to use the product rule, right? You can't just take derivative of each one. Derivative of f times g is f prime g plus g prime f. But when you're taking a limit of a product, it's equal to the product of the limits. You're allowed to split it. Now, why that's so important is because of what I'm about to write on the next step. I'm not doing L'Hopital, okay? I'm just going to say that limit right there is equal to the limit as x approaches 0. Let's see if you can tell what I do here. 2 secant squared x over 6 cosine x times the limit as x approaches 0 of sine x over x. Did y'all see what I did? This right here is that, right? 6 obviously is that. Where did this cosine x come from? I rewrote tangent as sine over cosine. And I put the cosine here, and I left the sine over here. And then this x comes from this x right here. Do you all see that? Why did I do that?
Because that's going to be 1 up there.
Yeah, look at this limit now. Is this limit causing a problem at all? What's secant of 0? 1 squared, 1. This is a 2, isn't it, up top? This limit right here is headed towards 2 over, what's cosine of 0? 1 times 6. That's headed to 2 over 6, right? That limit is not a problem. What about this limit? Where is it headed?
1.
Well, yes, but before that, it's what? It's 0 over 0, isn't it? But I can do L'Hopital on that one. We know it's going to be 1, right? But I can do L'Hopital here. So this will be equal to, by L'Hopital's rule on this guy right here, 2 over 6 times, what, limit as x goes to 0 of cosine x over 1, which is just 1. So what's the answer? 1/3. Can you appreciate how much trouble we saved ourselves by splitting that up? Yes? So my recommendation would be, if you're using L'Hopital, it starts to look like it's getting more complicated, but you see something in there that you could attack with L'Hopital, then just peel the parts off that aren't causing the problem and look at that as a separate limit. Got it? Could I have not done the sine over cosine? I could have, right? Another way someone could have split this up, they could have said that this is equal to the limit as x approaches 0. Could have just done the 2 secant squared over the sixth. Could have just done that. And then pulled the tangent x over x like that. You see that? That still would have been 0 over 0, right? And so I could have done L'Hopital right here. I would have got what? Secant squared x on top over 1, which would be 1 over 1. So you would have got the same answer. Just showing you there would have been, you know, a couple of ways you could have done that. All right, that's a good problem. All right, how about this one? Limit x approaches pi from the right side, or left side, sorry, of sine x over 1 minus cosine x. What do we do? Yeah, you might need to draw it if you want. Let's see, sine, you might want to go back and look at what sine is. Sine goes like this, right? This is pi in the middle, this is 2 pi out here. We're approaching pi from the left, so from this side, we're going down. Where is it approaching? It's approaching 0, right? So the top is approaching 0. The bottom is approaching, let's see, what is...
That negative 1 minus 1 is 0, right?
Yeah, do you know what cosine of pi is? Cosine of pi? Yeah, you have to... Do you want to look at the cosine function? We'll look at the cosine function if you want like this. You can also go off the unit circle.
Yeah.
Here's 2 pi. Here's pi in the middle. That's negative 1. You're approaching from the left, so negative 1? It's still approaching negative 1? So you've got 1 take away negative 1. 1 take away negative 1. That's 1 plus 1. That's 2. This is approaching 0 over 2. That's just 0. There's no problem here. Do y'all see that? There's no issue. You're done. Got it? What would have happened if we would have used L'Hopital's rule? What if we hadn't really analyzed this first and we were doing our homework and we were like, well, we know this section is about L'Hopital's rule, so I'm just going to start taking derivatives. Let's see what we would have got. If we would have done the L'Hopital incorrectly, right, this would be wrong. Let's see if we would get 0. Derivative of the top, cosine x. All right, derivative of the bottom, derivative of 1 is 0. That minus has to come with us. What's the derivative of cosine x? Minus sine x. Like that. Yeah, what would this be? This would be limit x approaches pi from the left of cosine x over sine x. And we can use the same pictures, right? What happens here? For the cosine function, as we approach pi from the left, we're going to what? Negative 1. And on the bottom, sine from the left, 0. Fixed over 0. Fixed over 0. It's either infinity or negative infinity or doesn't exist. Which one is it? No. Negative infinity? Okay, so the way we're getting that, the top is approaching a negative number, right? Negative 1? So top is negative. The bottom is approaching 0 on the sine curve from the left. So are these little positive numbers or negative numbers? These are little positive numbers, right? We're approaching 0, flat, but we're approaching it from above the x-axis. So these are approaching 0, but little positive numbers dividing into a negative number, you would say that this is going to negative infinity, right? And you'd be wrong, because the answer is 0.
I said it was 0.
Pardon?
I said it was 0.
Well, this wouldn't be, yeah, if you concluded from this that it was 0, then you would be getting it right by being wrong. This is not 0. We did these in the past. When you had a fixed number over 0, that there were 3 possible outcomes. Y'all good? All right. Feels like Monday, doesn't it? Oh, it is. That's right. That explains that. All right. So that gives you kind of the gist of how L'Hopital's rule works. But now it's time to go attack some different indeterminate forms. Limit x approaches pi over 2 from the left of secant x minus tangent x. Well, you need to know what secant of pi over 2 is. It is undefined, but it's approaching something. So this is really going to be kind of, I don't know, I'm looking around trying to figure out who knows how to graph secant x. Anyone know how to graph secant x? It's okay if you don't. How is it related? It's related to another function. What function is it related to? Cosine, right? It's the reciprocal of cosine? Yeah, so this is the way we do secant x. First we graph cosine. All right, and I'm going to do it in a different color. We graph cosine. We've got to know at least what cosine looks like. Right, that's what cosine looks like. Then to graph secant, what we do is everywhere that cosine is 0, we draw a vertical asymptote. This was in pre-cal, by the way. And then, at the bottoms of these valleys, we draw these little U's. This is secant. Does that look familiar? And then at the top of these hills, we've got U's that go like this also. And then we got a U over here that goes up like this and up like this. And these are stuck between 2 more vertical asymptotes. That's how you graph secant. I'd like to know what happens as you approach pi over 2 from the left. So here's pi, right? Here's pi over 2.
So it goes up to infinity.
Goes to infinity. So this is headed to infinity. Minus, now, what's tangent of pi over 2 as you approach pi over 2 from the left? So you got to know what tangent looks like. We just graphed that a second ago, didn't we? And wasn't this pi over 2 right here? What happens as you approach pi over 2 from the left? Goes to infinity also. So we have infinity minus infinity. That is an indeterminate form. Yes?
Oh, sorry. What was pi over 2 on the first graph?
Pi over 2 is right here. It's right there. Because look, this is pi. Pi over 2, 3 pi over 2. Make me tired. All right, so we have infinity minus infinity. What do we do here? Well, L'Hopital, but you can't use L'Hopital unless it's infinity over infinity or 0 over 0. So you can't just, L'Hopital's rule does not say that if you see this, then you just take derivative of each one. That is not the case. You got to have a ratio. It's got to be 0 over 0 or infinity over infinity. So I've got to somehow hopefully